Hey, welcome to the next channel. So often I get questions from students or else through my clients, especially something related to network optimization, very specific towards MTU optimization and stuff like that. So to demonstrate the same, I got some few Lego bricks so that we can discuss this in depth, so that we never know in which situation you may need it in terms of your building your network appliances. So this will be very useful in terms of architecting your networking products. In special cases, if you are doing some tunneling and various stuff, you have certain ways you can optimize overall and you can improve the network efficiency, because people often forget this factor, and they do focus a lot about TCP optimization. I often see in anytime anybody who talks about network acceleration or something, they just talk about TCP acceleration. They just don't consider the other big picture is like other protocols which are involved in any network channel. You get all sorts of protocols. It is not only TCP, it is going to flow through that channel. So this is what it is. So to demonstrate, I got various Lego bricks. As you can see here, what I did is I arranged in this way so that you have this large Lego piece, and then front you have this triangular shape. This depicts like a vehicle or something like that. So you can imagine this is like your network frame with all that layers, and finally you can add your payload on top of it. You can consider this payload as IPv4 packet on top of this the entire Ethernet header. You can imagine this as Ethernet header, or you can imagine this is with IP header and then TCP header or UDP header, and finally you can fit your application layer protocol part on top of it. So what I did is I did the various sizes. As you can see here, one is bit larger than this. You can see here this is much more larger than this, and then I have also done a bit smaller ones like this, and much more smaller one like this. So this will demonstrate. Let's consider each of this size determines your MTU, and whatever is vacant here is what you can put the extra bytes on top of it, so that once you fill this, it will constitute a single MTU. So let us imagine we take this smallest one, and let us imagine you just fit this brick, and what happens is technically assume this is some kind of long distance wireless communication or something, and it's not a reliable connectivity what you got. So you are restricting the MTU in that case, so that in case if there is any corruption of packets or any packet drops or any such events, what happens is there is going to be a small lossage in this packet alone. And what you can do is if you find this packet is not arriving at the remote end as the way TCP recovers, or else in the application layer protocol, even it is UDP, as the way it understands that there is something, there is yet to be received, not yet received, it can do a retransmission and it can pull that missing packet. So in such situations, essentially what happens is it is going to pull this packet once again, and it is going to work fine. But the question is, as the way you get much faster WAN networks, here is a situation you don't need to do this, because to send any sizable file you need to construct many such packets. I don't have another one with the same space. So you need to construct many such frames essentially, because this is, assume if it is data link layer included, this is a frame, not a packet. So you need to construct many such frames to send that size of file or content in a specific connection. Whereas in case if you have a much faster network like a gigabit network or something, you can have a much larger MTU, and then in case if you can adjust the overall size of the MTU in your custom network channel, it is good that you increase the size of MTU, so that in one specific transaction what you can do is, let me fit some of these bricks into this, and what happens is you can construct a packet somewhat like this. So let's assume this entire blue brick is one single chunk of bytes of a packet. So what happens is in one transaction you can send a lot of data, unlike this scenario. In this situation, you need to construct many such packets to send something sizable as equivalent as this, whereas in this situation you just need to send one packet. Since the network is much faster and sometimes it may be much reliable because it may be a wired fiber optic link or something like that, or some kind of data center connectivity or something. So in that situation you can construct much larger frames, and in case if any network corruption, in case any interference or some packet loss or anything is experienced, it can anyway reconstruct this and it can send it. But however, here is the situation, it also depends on how efficient is your source and destination server and client machines, because all these packets are maintained in the kernel space as the way it constructs in the IPv4 stack. If it is something you are sending it in TCP, then it has to keep a track of these arrived packets, and then any missing packets or out of order packets, it has to manage all these things. So there is going to be some amount of consideration you have to consider about that source and destination devices, not only about your network appliances in your networking network channel as such. So what happens is, in such situation, having said that, assume you have a very fast connectivity, you can send easily these large sized MTU frames, so that in case if that packet loss is very minimal, you get packet loss maybe couple of packets in an hour, then it is very economical. You can send in one transaction huge chunks of data to and fro, so that you don't need to unnecessarily spend a lot of time in constructing these small frames. So when you construct the small frames, your Ethernet header or whatever is going to be the same, whether it is this size to frame or this size to frame, or whether it is this size to frame. So you are wasting a lot of interframe delays. You are getting a lot of interframe delays and stuff like that, because once a frame is sent, you will have some time, there is some delay which is incurred, and after that you will get the next frame. Whereas you can compare a scenario like this. If you compare this frame versus this frame, you have very less losses in terms of interframe delay and other stuff, because you don't have such scenario at all. One shot you are sending a large frame, and then in every transaction such large frame will get transmitted. So this is what is the advantage. Whereas in case if you do tunneling or something, you can also have some scenarios, like you can have sometimes you may have like IP on IP or such tunneling. So in that situation, let's assume you have an extra IP header. Unfortunately, by doing such tunneling or any VPN situation, sometimes the MTU is going to be limited, and with that of course it is not going to be like in this factor, but it is going to have something very small some sizable amount will be taken up by those tunneling layers as you add. And that way what happens is, if you add any tunneling or something, of course you will get some loss of MTU, the amount you can send the real payload. So in that case, as the way the packet gets constructed, you can get a situation like this, you can get somewhat like this. So in this way it will be like a sort of hybrid packet which has many layers as the way it does tunneling. It depends on the mechanism you use to tunnel the same. So that way of course you need to compromise some amount in terms of MTU, but always you should understand the VPN technology. As the way you do tunneling, you have that bottleneck always. You will get your MTU will get limited, and sometimes if some packet arrives like this, and assume you do next you send some packet like this, and suddenly you send it through a VPN tunnel, and always it's going to be a worst case scenario. It has to dissect this entire packet, and then it has to dissect this entire packet as you can see here, and then it has to put these contents in a sort of VPN tunneled packet like this, and it has to construct the same. So these are various challenges, and it takes a lot of I can't say like only calculation or something. It takes a lot of practice, and you need to evaluate in a real time situation. You need to evaluate with various samples. I mean to say, you need to do a lot of trials, and then you need to evaluate how it behaves in that real time scenarios, and then you can work out a solution to solve in case if you feel MTU is going to be a bottleneck. But however, having said that, in case if you are a student, generally MTU it contributes a lot in terms of network performance and network optimization and the stuff like that. So MTU is a sort of factor which you have to always consider anytime you do deal with any mesh networks, wireless network and stuff like that. And this is not only limited with respect to networking technologies as such. This is also sometimes it also comes to a picture when it comes to storage technology. I sometime bought a Seagate drive, and then in that drive they mentioned that it has been done an advanced format. So when I checked, I mean they said like it's going to have an higher data rates, and the fact it gets higher data rates is due to advanced format. And then I visited their website, and then I read some cool documentation about the same. So what they claim is, if you go to the Seagate website, so here is the website. As you see here, it really looks similar to network packets. So what they claim is they have each frame constructed in this way, and they have done a comparison. Earlier they have done a 512 byte sector layout, as you can see here, which is a legacy. And they claim that, of course, just like network packets, so each of this frame is going to have that ECC and then other headers. You can see their gap, sync, and some address mark and stuff like that. I'm not a networking, I'm not a storage expert, so I can't really understand what their terms are, but I can really understand this. It all boils down at each transaction how many such chunks can be pulled out of the storage device to the operating system, as the way you read through storage drivers, or else how much you can push back to that storage hardware. So that's what it translates to. So if you understand this, it is same like your network packets. You have the ECC like any Ethernet frame, and then you have that main payload in which you can encapsulate your IPv6 packets or else IPv4 packets or anything like that. So if you see here, what they are saying is earlier it is 512 bytes, and now it is they are using a large 4K byte layout. So it is very apparent that by increasing the amount of size of this frame, or they may say this as a sector or whatever it is. So by increasing the size of that, what they are essentially avoiding is they are reducing that interframe gap. And then actually interframe gap is a sort of technical term. I think you can do a wiki about it. Interframe gap, it's gap, interframe gap, yeah, IPG. So you can see here, you can read about interframe gap, the terminology, and a lot of physics and maths involved in Wikipedia. So I highly recommend, in case you are doing any college research or something, or else a PhD or something, try to visit and read about this. It will really help in terms of doing this MTU and bandwidth calculations and stuff like that. So essentially you can see here, it is going to avoid all this extra gap and sync headers. By doing that, what they have done is they have eliminated everything, and then for this entire 4K byte, that whatever they represented here, all they have to do is they have to put only one gap, sync and address mark, and then followed by which one ECC. Instead you do again and again for 512 byte sized chunks. So essentially what they are doing is they have translated 1, 2, 3, 4, 5, 6, 7, 8, totally 8 chunks into a one large chunk. And this way what happens is, as the drive gets better and better, as the density or storage density increases, at every single transaction they can able to send more bytes at one shot. So this is what essentially is happening. So which is the reason I have done once plotting my drives in this database. I generally maintain all my working drives and also my expired drives and stuff like that. I have some of the drives which are almost a decade old, but the interesting thing is, this is what, if you notice, some of the drives are very old. You can see here one such drive is a very old drive. This is like 2009 I got. I'm not sure about the exact purchase date, but the manufacturing date is, as you can see here, it is 18 March 2009. So it's been used for so and so hours, and then you can see here its transfer speed is just around 70 Mbps. I don't want to kind of do every sort of parameter like seek and other latency factors. I just done a very simple HTTP PAM Linux benchmarking, and then I can able to find out a generic transfer rate. Maybe I think this is something related to its read performance. I'm not sure whether it is read write combined or else just read alone, but anyway it gives the rough idea. So if you compare this with any modern ones which I got here, you can see here 2015 I got this 3 TB drive. It has around 182 GB, and then there is another drive which I got a 4 TB drive which has around 160 Mbps. This is bytes per second. So if you compare these drives with this a decade old drive, you can see how much is this transfer speed increased. And also, yes, of course, it also matters whether it's a desktop drive or whether it's a NAS drive or else this portable laptop drive. So in case if you want to compare, there is also another portable drive. You can see here, this is also my laptop drive. So if you compare here, this is around more than 100 Mbps, 111 Mbps versus this drive which is very, very low. And the same thing happens in this case. There is a very old 250 GB drive. It has only just 55 Mbps, whereas in this case I have another laptop drive which is you can see here this this one is also a laptop drive, Western Digital Blue drive. This came with my Dell 15R laptop. So if you see here, it is giving around 114 Mbps. So this is what it is. So as the way technology improves, what they are essentially doing is they are increasing that the total chunk of data which it can be transferred at one instance from the operating system to the real storage hardware to and fro. So this is what it is. So essentially they are doing is increasing the speed, and of course we should also count other parameters like the drive speed and the density of the data you pack and the amount of the rate at which you read this data or write the data and stuff like that. But on the other side, even this is also a huge contributing factor, because you are not wasting time in terms of building all these smaller chunks and then transferring it one after another to and fro to that software layer, and then back to your real physical hardware to and fro. So this is what it is. So MTU is a huge contributing factor when it comes to network optimization. If it is a reliable network, sometimes you can use larger MTU sized packets. You can do various you can build your custom gateway so that you can customize this factor. It's just not TCP acceleration. It's just not about something you do in the TCP stack or something. It is not about that. I always consider what it is more important is network optimization, not just sideline and then only discuss about TCP or something. TCP may get obsolete after some time. Why do you need to think about that? You just need to get that big picture, and you need to solve as a whole. It is just not about TCP or something. It is just the networking is all about covering all aspects of network data. So this is what it is. So in that way, if you see, sometimes you may also have some more complicated scenarios. You may have a packet or frame within another frame. You can have something like this, and it may get encapsulated. In that case, you may have various other contents within the same, something like that. So it can be any such situation. So what happens is, deciding this MTU factor is very critical. It's just not so important in a LAN like situation, because here you don't have much issue of packets getting dropped unless until you have any loose connections or anything which is unreliable, or else you have a very long range Wi-Fi network in your home, something like that. In that situation, due to interference or something, packets may get corrupted, and of course you may lose some bandwidth in that way. But if you go start deploying long distance WAN networks, then this becomes a very crucial factor. You have to analyze, you have to use various tools and analyze what is essentially happening in your network, and you have to analyze in all factors. So this is what some of my core research goes into, and also as a part of my topic research. So this is something I do on mundane level, so that I can identify in which ways I can optimize the data. And also, if you have any situation, if my clients generally they say that this is the scenario at which things are connected, in that situation I generally analyze their existing networks, and then I see that in various angles that what could be the issue, that it is hampering that bandwidth, the way it is coming, and the latency eventually they are seeing in terms of that to and fro communication. So this is what it is. So hope you guys loved watching this video. So this is a huge topic. It's like almost we can sit and talk about it for many more hours. So this is what it is. So this is a huge topic. I generally like to cover various aspects and not just sticking with respect to storage, networking technologies. We can just take an example, something like this from storage technologies as well. So this is a huge thing. It's like how much you can transfer at any instance, how much size of chunk of data you transfer at any specific given instance. So it all depends on the physics, underlying physics. It's a faster network, you can optimize according to that. It's a slower network, you can optimize according to that. As the way technology improves, as the way we upgrade your networking devices and network hardware, you need to regulate this as well. Unfortunately, what is happening is we are still sticking towards that very outdated 1500 bytes MTU, and then I feel even we are sticking to the same outdated TCP IP and stuff like that. It is a high time that we need to think something beyond this mundane protocols which we are using almost for more than 3 to 4 decades by now. So that's what it is. So hope you guys loved watching this video. In case if you have any questions, in case if you like to discuss about something, send an email and we be in touch. Thank you once again for watching this video. Have a nice day. Bye bye.